Okay, so the next module is going to be all about equilibria and acidity. So to get us going, we're going to start talking about a series of molecules that have to do with acidic halogen molecules. So let's talk about some halogens and talk about how these molecules can be acidic. So these are the 4 different acids we're going to talk about. And just to remind everybody, when we talk about something being acidic, we're talking about Bronsted acid-base acidity. So that means it's all about whether a hydrogen is lost or gained. So if something is acting as an acid in terms of a Bronsted-Lowry way, we're talking about just how easy that molecule can lose H. If we actually wanted to look in the literature, we can try to find some numbers that try to quantify the acidity of each one of these molecules. You probably remember hearing about pKa. So pKa is our quantitation for just how acidic a molecule is. So we're going to look at pKa, but we're also going to look at electronegativity. And I'm just going to abbreviate electronegativity by En. And we said that we can utilize this kind of a periodic table to talk about electronegativity. So if you look at the halogens, you see that fluorine is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine. So if we wanted to draw a trend, we would say, okay, electronegativity, as you go from very low on the periodic table to very high on the periodic table, the electronegativity increases quite a bit. The first instinct a lot of students have is to try to relate electronegativity to acidity in the following way. Most people would say, okay, of these acids, HF is the most acidic molecule and HI is the least acidic molecule. And it turns out that this is actually incorrect. Okay, which is actually pretty surprising compared to what we just talked about at first glance, because your first impression 99% of the time for most people is to say, well, F is very electronegative, it should take the electrons from hydrogen. I is very, it's not as electronegative as fluorine, it shouldn't really take the electrons as well. And so for that reason, you would think that HF would be more acidic, but it's actually not. Okay, so let's actually get some numbers to back this up. So just in case you don't remember, the numbers for pKa, what they represent is as these numbers get smaller, the molecule gets more acidic. And even as the numbers go into the negative range, you continue to get more and more acidic. So what these numbers are telling you is 3 is obviously the biggest number, negative 12 is the least that you could have in this series. And so what we would then conclude from the numbers that we get from the literature is that the acidity actually gets higher as we go down the periodic table. So you would say that HI would be the most acidic, and then HF would be the least acidic. Okay, so don't fall in, long story short, don't fall into this trap of thinking that just because fluorine is the most electronegative atom, that HF is the most acidic acid in this series. If we want to, the thing that's held constant for each one of these molecules is the hydrogen. So if you want to think about how molecules bond together, they overlap their orbitals. And so if we wanted to represent that, we would say, okay, H would have this size orbital, and we'll just compare HF to HI. This will be our hydrogen atom for HI and HF. And as we go down the periodic table, the valence shell for iodine is actually much, much larger than the valence for fluorine. So if you envision how iodine and fluorine could bond to each other, you could envision the fluorine taking its orbital and trying to overlap it with the hydrogen right there. So you can envision, okay, these 2 orbitals are overlapping. Okay, and then we might have a little bit of dead space right here. And then if we compare and contrast to what this might look like for an iodine, the iodine valence orbital is much bigger, so it's going to look something like this. I'm trying to represent the dead space with this blue color. And this is our iodine right here. You can see that the majority of the iodine's orbital isn't actually overlapping with the hydrogen. And again, it's this overlap of orbitals which gives us, a very stable covalent bond. So the less overlap you have, the less strong the bond is going to be. So another way to think about it is if you imagined yourself trying to hold a ping pong ball in your hand, it's very easy for you to hold that ping pong ball. So if your hand is the hydrogen and the ping pong ball is the fluorine, it's very easy for your hand to hold on to that fluorine, versus if you imagine your hand trying to hold on to a basketball, it's very unlikely that your hand is going to be big enough to stably hold on to that basketball. So this is kind of the metaphor for this hydrogen to iodine overlap versus hydrogen to fluorine overlap.